Patients administering GLP-1 receptor agonists like semaglutide frequently report an unexpected and profound side effect: a sharp, unprompted decline in compulsive smartphone checking, endless digital notifications, and algorithmic feed scrolling. This unexpected cross-system impact occurs because these advanced metabolic medications are capable of crossing the blood-brain barrier, directly modulating the brain's core reward, salience, and motivation circuits. To understand why a therapeutic peptide engineered originally for type 2 diabetes and chronic weight management can drastically disrupt digital screen habits, we must examine the intersection of modern neurobiology, psychopharmacology, and software platform design. Short-form video apps, social media feeds, and mobile gaming interfaces are not built by accident. They are engineered using deep learning recommendation engines, such as TikTok's For You page architecture, explicitly designed to capture human attention and maximize engagement loops. Every time a user refreshes a digital feed, receives an unexpected push notification, or transitions seamlessly to another auto-playing video, the brain anticipates a potential reward. Psychologists and behavioral economists define this mechanism as a variable ratio reinforcement schedule, mirroring the exact unpredictable payout structure utilized in slot machines. Because the user never knows whether the next swipe will yield a boring post or an intensely entertaining viral video, the brain remains in a constant state of hyper-attentive anticipation. Deep within the midbrain, localized clusters of dopaminergic nerve cells fire rapid, transient bursts of neurotransmitters into a critical subcortical structure called the nucleus accumbens. This rapid electrochemical event is known as a phasic dopamine spike. These phasic spikes encode behavioral salience, teaching the brain that checking a glowing smartphone screen is vital for social connection, status, or immediate stimulation. Over time, this transforms a conscious, deliberate choice into an automated behavioral loop. The habit becomes deeply ingrained as synaptic connections are reinforced, eventually driving the user's hand to reach for their phone automatically, often before the prefrontal cortex, the thinking, executive control center of the brain, even has time to evaluate the action. For decades, endocrinologists and clinical pharmacologists believed that GLP-1 receptor agonists, including structural variants like semaglutide, tirzepatide, and liraglutide, acted almost exclusively within the gastrointestinal tract, the peripheral vagus nerve, and the hindbrain to signal physical satiety and slow gastric emptying. However, semaglutide possesses a unique chemical architecture that differentiates it from naturally occurring human GLP-1 hormones. Scientists modified its molecular structure by attaching a specific fatty acid chain that binds strongly to circulating albumin proteins in the blood. This structural adaptation dramatically extends its elimination half-life to roughly 165 hours, allowing the therapeutic peptide to remain biologically active in systemic circulation for over a week. Crucially, this extended half-life and modified molecular structure enable the drug to penetrate the blood-brain barrier. It enters the central nervous system via circumventricular organs, specialized brain regions with more permeable capillaries, and travels along ascending neural pathways connected to the vagus nerve. Once inside the central nervous system, semaglutide binds densely to GLP-1 receptors residing in key limbic and extralimbic structures involved in reward processing and motivation, including the ventral tegmental area, or VTA, the nucleus accumbens, the lateral hypothalamus, and the amygdala. This central accumulation triggers a profound cross-system overlap. The ancient evolutionary neural pathways governing the consumption of hyperpalatable, calorie-dense foods overlap directly with the modern neural circuits processing digital novelty, social validation, and endless mobile scrolling. Semaglutide does not induce global dopamine depletion, nor does it cause flatlined anhedonia or strip patients of their capacity to experience normal joy. Instead, it precisely recalibrates signaling fidelity by interacting directly with inhibitory interneurons known as GABAergic neurons. Within the ventral tegmental area, dopamine-producing nerve cells are tightly controlled by local GABA networks that act as the brain's neurochemical circuit breakers. When circulating semaglutide molecules attach to the GLP-1 receptors expressed on these GABAergic interneurons, they enhance their excitability and firing rate. Consequently, these cells release a higher volume of inhibitory gamma-aminobutyric acid, or GABA, into the local microenvironment, which suppresses the firing activity of neighboring dopaminergic neurons. Now consider what happens when a smartphone push notification appears, or a user opens a personalized social media feed. In an unmedicated state, that cue triggers a massive, sharp phasic dopamine spike in the nucleus accumbens, intensely reinforcing the checking behavior. Under the influence of semaglutide, elevated GABAergic tone acts as a functional damper. When a digital trigger occurs, the brain struggles to produce that powerful, addictive cellular burst. Instead of a sharp dopamine spike, the neural architecture registers a flattened, muted reward signal. Stripped of its powerful neurochemical payoff, the smartphone loses its compulsive psychological gravity. The constant, gnawing urge to pick up the device recedes into the background, a neurological phenomenon that clinical researchers and patients frequently compare to the silencing of food noise. Without the expected dopamine reward reinforcing the loop, the brain initiates a vital psychological process known as extinction learning. When habitual triggers, such as reaching for a phone out of sheer boredom or anxiety, fail to yield the anticipated neurochemical reward, the brain gradually begins to unlearn the habit. Over time, the old neural pathways atrophy and the intensity of the behavioral urge fades away. What began as scattered anecdotal reports from patients managing diabetes or obesity has now become an intense focus of modern biomedical and neuroscientific research. Clinical investigators are actively studying semaglutide, alongside newer dual GIP/GLP-1 receptor agonists and emerging oral small molecule compounds to determine their broader efficacy across various impulse control and compulsive disorders. These ongoing studies encompass alcohol use disorder, nicotine dependence, compulsive gambling, and excessive digital device addiction. By demonstrating that behavioral addictions, from compulsive eating to mindless digital scrolling, share identical neurochemical real estate with physical rewards, GLP-1 therapeutics have provided researchers with a powerful biological target for resetting reward systems that have become chronically oversensitized in the modern digital age. Have you or someone you know noticed unexpected shifts in habits, like less phone scrolling, reduced screen time, or fewer cravings, while taking a GLP-1 medication? Drop your experience in the comments below. If you want to dive deeper into how neurobiology shapes our digital lives, hit subscribe and check out our full breakdown on dopamine loops and modern addiction science. Thank you for watching, and we'll see you in the next video.